All right, welcome back. So let's implement our priority queue by copying what we've already done. So here's my max binary heap. I just copied it into a new file. And I'm going to first change the name, priority queue. And we're going to leave it as this.values. Then at the bottom or somewhere else, I'm going to define our class node. And node in the constructor takes in a value, call it val. And we just set this.val equals val. And then we also have, it also takes a priority. Whoops, did not add that in. There we go. Okay, so now we have each node has a value and an associated priority. Now we have two things we really need to do. The first is make sure we're comparing based off of priority everywhere rather than value. Or, well, not even value, rather than just the element itself, because we used to not be using this node class at all. We used to just insert things as is. So when we insert something, we're not just going to insert an element. We're going to insert something, so we're going to take a value and a priority, and then we're going to make a new node. So let's do new node equals new node, val, and priority. And then we're going to pass that in, this.values.push, instead of element, it's new node. So that's going to add it to the very end, and then we need it to bubble up, which is what we have here. So that's all good. But then when we look at bubble up, we have a small problem. Well, it's more than a small problem. Our code isn't going to work at all because we're not using priority. We're just comparing values directly. So index is going to be the same, element is fine, while index is greater than 0, parent index, this is all fine, but we want to compare if element.priority is less than or equal to parent.priority. We'll break. Otherwise, this.values, okay, and that's all the same. If we are trying to make this a min, so I'm actually going to leave this first as a max binary heap, and we'll come back to that. But just note, this is going to need to change. The other thing I forgot to do is change this to be NQ, which doesn't really matter. Oh, that's not how you spell it, is it? Is that it? I can never remember. I think that's it, yeah. No. There we go. So NQ, bubble up. All right, and then instead of extract max, we're going to have DQ. I think that's right, I hope. And we're going to, let's see, we're going to remove the 0th element. Well, we're going to swap, that's all fine. Then we're going to sync down. So in sync down, we are taking the element, that's all fine. The indices, everything's good here. But now what we need to check is right here. If left child dot priority is greater than element dot priority. If, and then same thing over here. Right here, right child dot priority greater than element dot priority. Same thing one more time. Left child dot priority. Okay, so remember right now this is a max binary heap still. First, I might have forgot something. Let's just make sure it works. So we're going to make a new, we'll call it, let's say we're in the hospital. So we'll call it ER equals new priority queue. And then we're going to do ER dot, instead of insert, it's now in queue. And the first thing we'll have is, I don't know, how about just common cold? The priority, if we're doing a max binary heap, how it is right now, this will be a low number, like let's say 1. And then let's do a couple more. Let's also do, how about gunshot wound? It's going to be a priority of like 5. And then we'll also have high fever will be a priority of 2. Okay, so let's try running this. And if we look at our ER, first let's just check out the order. Okay, so you can see gunshot wound. Then its first child is common cold. Its second child is high fever. That part doesn't matter, right? And it's not going to be in order with only 3 elements, most likely. But it will rearrange, hopefully, when we DQ. So let's check. ER.DQ, we would expect to get gunshot wound. All right. Next, we expect to get high fever, which we did. And then common cold. And then nothing. Okay, so that's working. We have a max binary heap where we're getting elements, based off of the largest number for the priority. If we wanted to switch it around, it's just a matter of coming up here and changing these less than signs to a greater than sign. Same thing. Where else is the other one? Here. Change that to a less than sign. We're just reversing our logic. And one other change we should make right here, instead of calling this variable max that we're removing, it's now refers to the min. It doesn't actually make a difference functionally, but it's just nice to call it min instead. Okay, so let's do our same thing, except now I'm going to change these priority numbers because something like a gunshot wound will have priority level 1. That's high priority. A cold maybe we'll have like 5. A high fever, we'll give it priority of 4. Let's do a couple more. Let's do common cold. How about gunshot wound? I don't know, broken arm. So that will be pretty high priority, but not the same as a gunshot. So let's give that priority of 2. And then also, let's do another priority of, let's do 3. So middle priority, not that bad. Let's say like glass in foot. I don't know. Okay, so I don't know if this ordering actually makes sense. So I'm going to run the code, and we're going to do our first DQ. And what would we expect? Well, we want the value that has the lowest priority, gunshot wound. All right, that worked. Next, we expect the value with the next lowest, which is broken arm. Then glass in foot, then high fever, then common cold. So you can see that it doesn't matter what order we inserted them in, it's all about the priority. And it's giving us the highest priority element, or the lowest value priority, but the highest actual priority at any moment. And it's a min binary heap now. It's logically the same thing. We just changed some comparisons and renamed a variable from max to min. Otherwise, it's the same idea. Now, one thing that we should consider is what if something has the same priority? Like if there are 2 elements in here with the same priority? Well, right now our code doesn't guarantee that they actually would be returned based off of insertion order. So if it's a queue, so you would expect it, for example, if someone with a common cold got there first, and then we have another person who has another common cold, same priority level, you would expect to serve or help this person first. And you can add logic to make that work, but by default with our heap, it's not going to work that way. There's no guaranteed order between siblings, between things that are on the same level of a tree, or of a heap, technically a tree. But in our heap, it's just that a parent has a relationship with its 2 children, but the 2 children aren't necessarily, the siblings aren't in a particular order. So what we could do is add logic basically to add in a time here. So we could do like this dot, insert time equals date dot now or something like that. And then when we're comparing, instead of just comparing the priority, we would also say if the priority is identical, which one of these was inserted first. And then we would swap based off of that. But that's not really that important at this point because the actual algorithm for your priority queue, the comparison itself, will likely change if you're ever actually writing one. In the real world, it's usually not just a priority level. It might be a priority level plus how many resources it takes up or how resource intensive it is, plus how long it's been waiting. These different things that might impact the comparison rather than just a direct priority versus priority. Anyway, here's our priority queue. It's a min binary heap that's powering it, or that we're actually implementing it with. You insert things using enqueue, and whatever order they go in, it doesn't matter. It's based off of their priority level. Pretty nifty, I think. Much, much better than trying to do this with an array or a list and just traversing the entire thing to find the next item with the lowest or highest number. This is much faster. We're going to talk about big O, but it is log n for time complexity for insertion and removal. All right, priority queue done.